स्टूडेंट्स प्लीज शेयर दिस ऑडियो बुक एज मच एज पॉसिबल। आप लोग अपने दोस्तों से जितना ज़्यादा शेयर करोगे उतना ज़्यादा सभी बच्चों को बेनिफिट मिलेगा इसका, क्योंकि बहुत से बच्चे ऐसे हैं जिनको अभी नहीं मालूम चल पा रहा है कि ऑडियो बुक्स भी अवेलेबल हैं, तो उन तक भी ये चीज़ पहुंचे। इसलिए इसको जितना ज़्यादा आप शेयर कर सकते हैं प्लीज़ शेयर करिए। और एक बात और, आप सभी लोग मुझे कमेंट सेक्शन में बताते हैं कि हाँ मैम ये चैप्टर्स की पहले प्रोवाइड कर दीजिए, ये चैप्टर्स की। तो मैं सभी की विशेष तो नहीं पूरी कर सकती हूँ, बट मेरी कोशिश ये होती है कि मैं डेली आप लोगों को एटलीस्ट एक चैप्टर की ऑडियो बुक तो दे दूँ। हालांकि ऑडियो बुक बनाने में, देखने में ईजी लगती है, बट इसमें काफ़ी ज़्यादा टाइम लगता है, रिकॉर्डिंग करनी पड़ती है और इसकी रिकॉर्डिंग कभी भी एक बार में पूरी नहीं हो पाती है। और साथ ही साथ में जब रिकॉर्डिंग हो जाती है उसके बाद में इसकी एडिटिंग होती है और एडिटिंग में मुझे वापस से सारा सब कुछ फिर से सुनना होता है, तो इसमें थोड़ा सा टाइम लगता है। तो बी पेशेंट, थोड़ा सा धैर्य रखें। आप लोगों को एग्जाम के पहले सारी मिल जाएगी केमिस्ट्री की आपकी ऑडियो बुक्स, और बस इसको आप लोग जितना ज्यादा शेयर कर सकते हो उतना शेयर करो, ये मेरी आपसे हम्बल रिक्वेस्ट है। ओके, तो चलिए आज की स्टार्ट करते हैं। यूनिट 8, द डी एंड एफ ब्लॉक एलिमेंट्स। Iron, copper, silver and gold are among the transition elements that have played important roles in the development of human civilization. The inner transition elements such as TH, Pa and U are excellent sources of nuclear energy in modern times. The D block of the periodic table contains the elements of the groups 3 to 12 in which the d orbitals are progressively filled in each of the 4 long periods. The F block consists of elements in which 4f and 5f orbitals are progressively filled. They are placed in separate panel at the bottom of the periodic table. The names transition metals and inner transition metals are often used to refer to the elements of D and F block respectively. There are many 4 series of the transition metals: 3D series Sc2Zn, 4D series Y2CD, 5D series La and HF2Hg, and 6D series which has actinium and elements from Rf to Cn. The 2 series of the inner transition metals, that is 4f, that is Ce2Lu, and 5f, that is Th2Lr, are known as lanthanoids and actinoids respectively. Originally, the name transition metals were derived from the fact that their chemical properties were transitional between those of S and P block elements. Now, according to IUPAC, transition metals are defined as metals which have incomplete d subshell either in neutral atom or in their ions. Zinc, cadmium and mercury of group 12 have full D10 configuration in their ground state as well as in their common oxidation states and hence are not regarded as transition metals. However, being the end members of the 3D, 4D and 5D transition series respectively, their chemistry is studied along with the chemistry of the transition metals. The presence of partially filled d or f orbitals in their atoms make transition elements different from that of the non-transition elements. Hence, transition elements and their compounds are studied separately. However, the usual theory of valence as applicable to the non-transition elements can be applied successfully to the transition elements also. Various precious metals such as silver, gold and platinum and industrially important metals like iron, copper and titanium belong to the transition metal series. In this unit, we shall first deal with the electronic configuration, occurrence and general characteristics of transition elements with special emphasis on the trends in the properties of the first row 3D transition metals along with the preparation and properties of some important compounds. This will be followed by the consideration of certain general aspects such as electronic configurations, oxidation states, chemical reactivity of the inner transition metals. The transition elements D block. 8.1 Position in the periodic table. The D block occupies the large middle section of the periodic table, flanked between S and P blocks in the periodic table. The d orbitals of the penultimate energy level of atoms receive electrons, giving rise to 4 rows of the transition metals, that is 3D, 4D, 5D and 6D. All these series of transition elements are shown in table 8.1. 8.2 Electronic configuration of the d block elements. In general, the electronic configuration of outer orbitals of these elements is n-1 in bracket D1 to 10, Ns 1 to 2. The n-1 stands for the inner d orbitals, which may have 1 to 10 electrons, and the outermost ns orbitals may have 1 or 2 electrons. However, this generalization has several exceptions because of very little energy difference between n-1 d and ns orbitals. Furthermore, half and completely filled sets of orbitals are relatively more stable. A consequence of this factor is reflected in the electronic configurations of chromium and copper in the 3D series. For example, consider the case of chromium, which has 3d5-4s1 configuration instead of 3d4-4s2. The energy gap between the two sets 3d and 4s of orbitals is small enough to prevent electron entering the 3d orbitals. Similarly, in case of copper, the configuration is 3d10-4s1 and not 3d9-4s2. The ground state electronic configuration of the outer orbitals of transition elements are given in table 8.1. The electronic configurations of outer orbitals of Zn, cadmium, Hg and Cn are represented by the general formula n-1 d10 ns2. The orbitals in these elements are completely filled in the ground state as well as in their common oxidation states. Therefore, they are not regarded as transition elements. The d orbitals of the transition elements protrude to the periphery of an atom more than the other orbitals, that is s and p. Hence, they are more influenced by the surroundings as well as effect of the atoms or molecules surrounding them. In some respects, ions of given Dn configuration, that is n is equals to 1 to 9, have similar magnetic and electronic properties. With partially filled d orbitals, these elements exhibit certain characteristic properties such as display of a variety of oxidation states, formation of colored ions, and entering into the complex formation with a variety of ligands. The transition metals and their compounds also exhibit catalytic property and paramagnetic behavior. All these characteristics have been discussed in detail later in this unit. There are greater similarities in the properties of the transition elements of a horizontal row in contrast to the non-transition elements. However, some group similarities also exist. We shall first study the general characteristics and their trends in the horizontal rows, particularly 3D row, and then consider some group similarities. We will discuss the properties of elements of first transition series only in the following sections. 8.3 General properties of the transition element, D block. 8.3.1 Physical properties. Nearly all the transition elements display typical metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster, with the exceptions of Zn, Cd, Hg and Mn. They have one or more typical metallic structures at normal temperatures. The transition metals, with the exception of Zn, Cd and Hg, are very hard and have low volatility. Their melting and boiling points are high. Figure 8.1 depicts the melting points of transition metals belonging to 3D, 4D and 5D series. The high melting points of these metals are attributed to the involvement of greater number of electrons from n-1d in addition to the ns electrons in the interatomic metallic bonding. In any row, the melting points of these metallic rise to a maximum at d5 except for anomalous values of Mn and Tc, and fall regularly as the atomic number increases. They have high enthalpies of atomization, which are shown in figure 8.2. The maxima at about the middle of each series indicate that one unpaired electron per d orbital is particularly favorable for strong interatomic interaction. In general, greater the number of valence electrons, stronger is the resultant bonding, since the enthalpy of atomization is an important factor in determining the standard electrode potential of metals with very high enthalpy of atomization, that is very high boiling point, tend to be noble in their reactions. See later for electrode potentials. Another generalization that may be drawn from figure 8.2 is that the metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor in accounting for the occurrence of much more frequent metal-metal bonding in compounds of the heavy transition metals. 8.3.2 Variation in atomic and ionic size of transition metals. In general, of the same charge in a given series show progressive decrease in radius with increasing atomic number. This is because the new electron enters a d orbital each time the nuclear charge increases by unity. It may be recalled that the shielding effect of a d electron is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radius decreases. The same trend is observed in the atomic radii of a given series. However, the variation within a series is quite small. An interesting point emerges when atomic sizes of one series are compared with those of the corresponding elements in the other series. The curves in figure 8.3 show an increase from the first 3D to the second 4D series of the elements, but the radii of the third 5D series are virtually the same as those of the corresponding members of the second series. This phenomenon is associated with the intervention of the 4f orbital, which must be filled before the 5D series of elements begin. The filling of 4f before 5D orbital results in a regular decrease in atomic radii called Lanthanoid Contraction, which essentially compensate for the expected increase in atomic size with increasing atomic number. The net result of the Lanthanoid Contraction is that the second and the third D series exhibit similar radii. Example: ZR 160 pm, HF 159 pm, and have very similar physical and chemical properties, much more than that expected on the basis of usual family relationship. The factor responsible for the Lanthanoid contraction is somewhat similar to that observed in an ordinary transition series and is attributed to similar cause, that is the imperfect shielding of one electron by another in the same set of orbitals. However, the shielding of one 4f electron by another is less than that of one d electron by another. And as the nuclear charge increases along the series, there is fairly regular decrease in the size of the entire 4f orbitals. The decrease in metallic radius coupled with increase in atomic mass results in general increase in the density of these elements. Thus, from titanium Z is equals to 22 to copper Z is equals to 29, the significant increase in the density may be noted. Table 8.2 Electronic configuration and some other properties of the first series of transition elements. 8.3.3 Ionization enthalpies. There is an increase in ionization enthalpy along each series of the transition element from left to right due to an increase in nuclear charge which accompanies the filling of the inner d orbitals. Table 8.2 gives the values of the first three ionization enthalpies of the first series of transition elements. These values show that the successive enthalpies of these elements do not increase as steeply as in the case of non-transition elements. The variation in ionization enthalpy along a series of transition elements is much less in comparison to the variation along a period of non-transition elements. The first ionization enthalpy in general increases, but the magnitude of the increase in the second or third ionization enthalpies for the successive elements is much higher along a series. The irregular trend in the first ionization enthalpy of the metals of 3D series, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3D orbitals. You have learned that when d block elements form ions and s electrons are lost before d electrons, as we move along the period in 3D series, we see that nuclear charge increases from scandium to zinc, but electrons are added to the orbital of inner subshell, that is 3D orbitals. These 3D electrons shield the 4s electrons from the increasing nuclear charge somewhat more effectively than the outer shell electron can shield one another, therefore the atomic radii decrease less rapidly. Thus, ionization energy increase only slightly along the 3D series. The doubly or more highly charged ions have d-n configuration with no 4s electrons. A general trend of increasing values of second ionization enthalpy is expected as the effective nuclear charge increases because one d electron does not shield other electron from the influence of nuclear charge because d orbitals differ in direction. However, the trend of a steady increase in second and third ionization enthalpy breaks for the formation of Mn2 positive and Fe3 positive respectively. In both the cases, ions have d5 configuration. Similar breaks occur at corresponding elements in the later transition series. The interpretation of variation in ionization enthalpy for an electronic configuration Dn is as follows. The three terms responsible for the value of ionization enthalpy are attraction of each electron towards nucleus, repulsion between the electrons, and the exchange energy. Exchange energy is responsible for the stabilization of energy state. Exchange energy is approximately proportional to the total number of possible pairs of parallel spins in the degenerate orbitals. When several electrons occupy a set of degenerate orbitals, the lowest energy state corresponds to the maximum possible extent of single occupation of orbital and parallel spins. The loss of exchange energy increases the stability. As the stability increases, the ionization becomes more difficult. There is no loss of exchange energy at D6 configuration. Mn positive have 3d5 4s1 configuration, and configuration of chromium positive is d5. Therefore, ionization enthalpy of Mn positive is lower than chromium positive. In the same way, Fe2 positive has d6 configuration and Mn2 positive has 3d5 configuration. Hence, ionization enthalpy of Fe2 positive is lower than the Mn2 positive. In the other words, we can say that the third ionization enthalpy of Fe is lower than that of Mn. The lowest common oxidation state of these metals is +2 to form M2 positive ions from the gaseous atoms. The sum of the first and second ionization enthalpy is required in addition to the enthalpy of atomization. The dominant term is the second ionization enthalpy, which shows unusually high values for chromium and copper, where M positive ions have D5 and D10 configurations respectively. The value for Zn is correspondingly low as the ionization causes the removal of one s electron, which results in the formation of a stable D10 configuration. The trend in the third ionization enthalpy is not complicated by the 4s orbital factor, shows the greater difficulty of removing an electron from the D5, Mn2 positive, and D10, that is Zn2 positive ions. In general, the third ionization enthalpies are quite high. Also, the high values for third ionization enthalpies of copper, nickel, and zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements. Although ionization enthalpies give some guidance concerning the relative stabilities of oxidation states, this problem is very complex and not amenable to ready generalization. 8.3.4 Oxidation states. One of the notable features of transition element is the great variety of oxidation states these may show in their compounds. Table 8.3 lists the common oxidation states of the first row transition elements. The elements which give the greatest number of oxidation states occur in or near the middle of the series. Manganese, for example, exhibit all the oxidation states from +2 to +7. The lesser number of oxidation states at the extreme ends stems from either too few electrons to loss or share Sc2Ti or too many d electrons, hence fewer orbitals available in which to share electrons with others. For higher valence, that is Cu and Zn, thus early in the series scandium second is virtually unknown and titanium fourth is more stable than titanium third or titanium second. At the other end, the only oxidation state of zinc is +2. The maximum oxidation state of reasonable stability correspond in value to the sum of the s and d electrons up to manganese, followed by a rather abrupt decrease in stability of higher oxidation states, so that the typical species to follow are Fe second, third, cobalt second, third, nickel second, copper first, second, Zn second. The variability of oxidation states, a characteristic of transition elements, arises out of incomplete filling of d orbitals in such a way that their oxidation states differ from each other by unity. Example, V second, V third, V fourth, V5. This is in contrast with the variability of oxidation states of non-transition elements, where oxidation states normally differ by a unit of 2. An interesting feature in the variability of oxidation states of the d block elements is noticed among the groups 4 through 10. Although In the p block, the lower oxidation states are favored by the heavier members due to the inert pair effect. The opposite is true in the groups of D block. For example, in group 6, MO and W are found to be more stable than chromium 6. Thus, chromium 6 in the form of dichromate in acidic medium is a strong oxidizing agent, whereas MoO3 and WO3 are not. Low oxidation state are found when a complex compound has ligands capable of pi acceptor character in addition to the sigma bonding. For example, in NiCO4 and FeCO5, the oxidation state of nickel and iron is 0. 8.3.5 Trends in the M2 positive / M standard electrode potential. Table 8.4 contains the thermochemical parameters related to the transformation of the solid metal atoms to M2 positive ions in solution, and there is standard electrode potential. The observed values of electrode potential and those calculated using the data of table 8.4 are compared in figure 8.4. The unique behavior of copper having a positive electrode potential accounts for its inability to liberate H2 from acids. Only oxidizing acids, nitric and hot concentrated sulfuric, react with Cu, the acids being reduced. The high energy to transform Cu to Cu2 positive is not balanced by its hydration enthalpy. The general trend towards less negative electrode potential values across the series is related to the general increase in the sum of the first and second ionization enthalpies. It is interesting to note that the value of electrode potential for Mn, nickel and Zn are more negative than expected from the trend. 8.3.6 Trends in the M3 positive / M2 positive standard electrode potential. An examination of electrode potential values shows the varying trends. The low value of scandium reflects the stability of scandium 3 positive, which has a noble gas configuration. The highest value for Zn is due to the removal of an electron from the stable D10 configuration of Zn2 positive. The comparatively high value of Mn shows the Mn2 positive is particularly stable, whereas comparatively low value of Fe shows the extra stability of Fe3 positive. The comparatively low value for V is related to the stability of V2 positive. 8.3.7 Trends in stability of higher oxidation state. Table 8.5 shows the stable halides of the 3D series of transition metals. The highest oxidation numbers are achieved in TiX4s, that is tetrahalides, VF5 and CrF6. The +7 state for Mn is not represented in simple halides, but MnO3F is known. And beyond Mn, no metal has a trihalide except FeX3 and COF3. The ability of fluorine is to stabilize the highest oxidation state is due to either higher lattice energy, as in the case of COF3, or higher bond enthalpy terms for the higher covalent compounds, example VF5 and CrF6. Although V plus 5 is represented only by VF5, the other halides however undergo hydrolysis to give oxohalides VOX3. Another feature of fluorides is their instability in the low oxidation states, example VX2, where X is chlorine, bromine or iodine. And the same applies to COX. On the other hand, all Cu second halides are known except the iodide. In this case, U2 positive oxidizes I negative to I2. 2 Cu2 positive plus 4 I negative gives out Cu2 I2 plus I2. However, many copper compounds are unstable in aqueous solution and undergo disproportionation. 2 Cu positive gives out Cu2 positive plus Cu. The stability of Cu2 positive rather than Cu positive is due to the much more negative delta hydration H negative of Cu2 positive than Cu positive, which more than compensates for the second ionization enthalpy for copper. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. The highest oxidation number in the oxides coincides with the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxides of Fe above Fe2O3 are known, although ferrates FeO4 2 negative are formed in alkaline media, but they readily decompose to Fe2O3 and O2. Besides the oxides, oxocations stabilize V5 as VO2 positive, V6 as VO2 positive, and Ti4 as TiO2 positive. The ability of oxygen to stabilize these high oxidation states exceeds that of fluorine. Thus, the highest Mn fluoride is MnF4, whereas the highest oxide is Mn2O7. The ability of oxygen to form multiple bonds to metals explain its superiority. In the covalent oxide Mn2O7, each Mn is tetrahedrally surrounded by oxygens, including a MnO-Mn bridge. The tetrahedral MO4 and negative ions are known for V5, Cr6, Mn5, Mn6, and Mn7. Table 8.6 Oxides of 3D metals. 8.3.8 Chemical reactivity and E negative values. Transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble, that is, they are unaffected by single acids. The metals of the first series, with the exception of copper, are relatively more reactive and are oxidized by 1m H positive, though the actual rate of which these metals react with oxidizing agents like hydrogen ion is sometimes slow. For example, titanium and vanadium in practice are passive to dilute non-oxidizing acids at room temperature. The E negative values for M2 positive / M indicate a decreasing tendency to form divalent cations across the series. This general trend towards less negative E negative values is related to the increase in the sum of the first and second ionization enthalpy. It is interesting to note that the E negative values for Mn, Ni and Zn are more negative than expected from the general trend, whereas the stabilities of half-filled D subshell D5 in Mn2 positive and completely filled D subshell D10 in zinc are related to their E values. For nickel, E negative value is relatively to the highest negative enthalpy of hydration. 8.3.9 Magnetic properties. When a magnetic field is applied to a substances, mainly two types of magnetic behavior are observed: diamagnetism and paramagnetism. Diamagnetic substances are repelled by the applied field, while the paramagnetic substances are attracted. Substances which are attracted very strongly are said to be ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetism. Many of the transition metal ions are paramagnetic. Paramagnetism arises from the presence of unpaired electrons. Each such electron having a magnetic moment associated with its spin angular momentum and orbital angular momentum. For the compounds of the first series of transition metals, the contribution of the orbital angular momentum is effectively quenched and hence is of no significance. For these, the magnetic moment is determined by the number of unpaired electrons and is calculated by using the spin-only formula, that is, mu is equals to under root n in bracket n plus 2. Where n is the number of unpaired electrons and mu is the magnetic moment in units of Bohr magneton, that is Bm. A single unpaired electron has a magnetic moment of 1.73 Bohr magnetons. The magnetic moment increases with the increasing number of unpaired electrons. Thus, the observed magnetic moment gives a useful indication about the number of unpaired electrons present in the atom, molecule or ion. The magnetic moments calculated from the spin-only formula and those derived experimentally for some ions of the first row transition elements are given in table 8.7. The experimental data are mainly for hydrated ions in solution or in the solid state. 8.3.10 Formation of colored ions. When an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. This frequency generally lies in the visible region. The color observed corresponds to the complementary color of the light absorbed. The frequency of the light absorbed is determined by the nature of the ligand. In aqueous solutions, where water molecules are the ligands, the colors of the ions observed are listed in table 8.8. A few colored solutions of D block elements are illustrated in figure 8.5. 8.3.11 Formation of complex compounds. Complex compounds are those in which the metal ions bind a number of anions or neutral molecules, giving complex species with the characteristic properties. A few examples are FeCN6 whole 3 negative, FeCN6 4 negative, CuNH3 whole 4 2 positive, and PtCl4 2 negative. The chemistry of complex compound is within detail in Unit 9. The transition metals form a large number of complex compounds. This is due to the comparatively smaller sizes of the metal ions, their high ionic charges, and the availability of d orbitals for bond formation. 8.3.12 Catalytic Properties. The transition metals and their compounds are known for their catalytic activity, and this activity is ascribed to their ability to adopt multiple oxidation states and to form complexes. Vanadium oxide, finely divided iron, and nickel are some of the examples. Catalysts at a solid surface involve the formation of bonds between reactant molecules and atoms of the surface of the catalyst. This has the effect of increasing the concentration of the reactants at the catalyst surface and also weakening of the bonds in the reacting molecules, and that is the activation energy is lowering. Also, because the transition metal ions can change their oxidation state, they become more effective as catalyst. For example, iron third catalyzes the reaction between iodide and persulfate ion. 2I negative plus S2O8 2 negative gives out I2 plus 2SO4 2 negative. An explanation of this catalytic action can be given as 2Fe3 positive plus 2I negative gives out 2Fe2 positive plus I2, 2Fe2 positive plus S2O8 2 negative gives out 2Fe3 positive plus 2SO4 2 negative. 8.3.13 Formation of interstitial compound. Interstitial compounds are those which are formed when small atoms like hydrogen, carbon or nitrogen are trapped inside the crystal lattices of metals. They are usually non-stoichiometric and are neither typically ionic nor covalent. For example, TiC, Mn4n, Fe3H, VH0.56 and TiH1.7 etc. The formulas quoted do not, of course, correspond to any normal oxidation state of the metal. Because of the nature of their composition, these compounds are referred to as interstitial compounds. The principal physical and chemical characteristics of these compounds are as follows. Number 1, they have high melting points, higher than those of pure metals. Number 2, they are very hard. Some borides approach diamond in hardness. Number 3, they retain metallic conductivity. Number 4, they are chemically inert. 8.3.14 Alloy formation. An alloy is a blend of metals prepared by mixing the components. Alloys may be homogeneous solids, solutions in which the atoms of one metal are distributed randomly among the atoms of the other. Such alloys are formed by atoms with metallic radii that are within about 15% of each other. Because of similar radii and other characteristics of transition metals, alloys are readily formed by these metals. The alloys so formed are hard and have often high melting points. The best known are ferrous alloys. Chromium, vanadium, tungsten, molybdenum and manganese are used for the production of a variety of steels and stainless steels. Alloys of transition metals with non-transition metals such as brass, that is copper zinc, and bronze, that is copper tin, are also of considerable industrial importance. 8.4 Some important compounds of transition elements. 8.4.1 Oxides and oxyanions of metals. These oxides are generally formed by the reaction of metals with oxygen at high temperatures. All the metals except scandium form MO oxides which are ionic. The highest oxidation number in the oxides coincides with the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxides of iron above Fe2O3 are known. Besides the oxides, the oxocations stabilizes V5 as VO2 positive, V6 as VO2 positive and Ti4 as TiO2 positive. As the oxidation number of a metal increases, ionic character decreases. In the case of Mn2O7 is a covalent green oil. Even CrO3 and V2O5 have low melting points. In these higher oxides, the acidic character is predominant. Thus, Mn2O7 gives HMNO4 and CrO3 gives H2CrO4 and H2Cr2O7, V2O5 is however amphoteric, though mainly acidic, and it gives VO4 3 negative as well as VO2 positive salts. In vanadium, there is gradual change from the basic V2O3 to less basic V2O4 and to amphoteric V2O5. V2O4 dissolves in acid to give VO2 positive salt. Similarly, V2O5 reacts with alkalis as well as acids to give VO4 3 negative and VO4 positive respectively. The well-characterized CRO is basic, but Cr2O3 is amphoteric. Potassium dichromate K2Cr2O7. Potassium dichromate is a very important chemical used in leather industry and as an oxidant for preparation of many azo compounds. Dichromates are generally prepared from chromate, which in turn are obtained by the fusion of chromite ore, that is FeCr2O4, with sodium or potassium carbonate in free access of air. The reaction with sodium carbonate occurs as follows: 4FeCr2O4 plus 8Na2CO3 plus 7O2 gives out 8Na2CrO4 plus 2Fe2O3 plus 8CO2. The yellow solution of sodium chromate is filtered and acidified with sulfuric acid to give a solution from which orange sodium dichromate Na2Cr2O7 into 2H2O can be crystallized, and the reaction is 2Na2CrO4 plus 2H gives out Na2Cr2O7 plus 2NaIn plus H2O. Sodium dichromate is more soluble than potassium dichromate. The latter is therefore prepared by treating the solution of sodium dichromate with potassium chloride. Na2Cr2O7 plus 2KCl gives out K2Cr2O7 plus 2NaCl. Orange crystals of potassium dichromate crystallize out. The chromates and dichromates are interconvertible in aqueous solution depending upon pH of the solution. The oxidation state of chromium in chromate and dischromate is the same. Reactions are 2CrO4 2 negative plus 2H ion gives out Cr2O7 2 negative plus H2O. Next reaction is Cr2O7 2 negative plus 2OH ion gives out 2CrO4 2 negative plus H2O. The structures of chromate ion CrO4 2 negative and the dichromate ion Cr2O7 2 negative are shown below. The chromate ion is tetrahedral, whereas the dichromate ion consists of two tetrahedra sharing one corner with CrO-Cr bond angle of 126 degree. Sodium and potassium dichromates are strong oxidizing agents. The sodium salt has a greater solubility in water and is extensively used as an oxidizing agent in organic chemistry. Potassium dischromate is used as a primary standard in volumetric analysis. In acidic solution, its oxidizing action can be represented as follows. Cr2O7 2 negative plus 14H ion plus 6 electron gives out 2Cr3 positive plus 7H2O. Thus, acidified potassium dichromate will oxidize iodides to iodine, sulfides to sulfur, tin second to tin fourth, and iron second salts to iron third. The half reactions are noted below. 6I negative gives out 3I2 plus 6 electron. 3SN2 positive gives out 3SN4 positive plus 6 electron. 3H2S gives out 6H positive plus 3S plus 6 electron. And 6Fe2 positive gives out 6Fe3 positive plus 6 electron. The full ionic equation may be obtained by adding the half reaction for potassium dichromate to the half reaction for the reducing agent. For example, Cr2O7 2 negative plus 14H ion plus 6Fe2 positive gives out 2Cr3 positive plus 6Fe3 positive plus 7H2O. Potassium permanganate KMnO4. Potassium permanganate is prepared by fusion of MnO2 with an alkali metal hydroxide and an oxidizing agent like KNO3. This produces the dark green K2MnO4, which disproportionates in a neutral or acidic solution to give permanganate. 2MnO2 plus 4KOH plus O2 gives out 2K2MnO4 plus 2H2O. 3MnO4 2 negative plus 4H ion gives out 2MnO4 negative plus MnO2 plus 2H2O. Commercially, it is prepared by the alkaline oxidative fusion of MnO2 followed by the electrolytic oxidation of magnetate. And the reaction is MnO2, when it is fused with KOH oxidized with air or KNO3, it gives out MnO4 2 negative, that is magnetate ion. Next reaction is MnO4 2 negative, that is magnate, and electrolytic oxidation in alkaline solution, and it forms MnO4 negative, that is permanganate ion. In the laboratory, a manganese second ion salt is oxidized by peroxodisulfate to permanganate, and the reaction is 2Mn2 positive plus 5S2O8 2 negative plus 8H2O gives out 2MnO4 negative plus 10SO4 2 negative plus 16H Potassium permanganate forms dark purple, almost black crystals which are isostructural with those of KClO4. The salt is not very soluble in water, 6.4 gram per 100 gram of water at 293 Kelvin. But when heated it decomposes at 513 Kelvin. The reaction is 2KMnO4 gives out K2MnO4 plus MnO2 plus O2. It has two physical properties of considerable interest, its intense color and its diamagnetism along with temperature dependent weak paramagnetism. These can be explained by the use of molecular orbital theory which is beyond the present scope. The magnate and permanganate ions are tetrahedral. The pi bonding takes place by overlap of p orbitals of oxygen with d orbitals of manganese. The green manganate is paramagnetic because of one unpaired electron, but the paramagnate is diamagnetic due to the absence of unpaired electron. Acidified permanganate solution oxidizes oxalates to carbon dioxide, that is iron second to iron third, nitrides to nitrates and iodides to free iodine. The half reactions of reductants are 5COO negative single bond COO negative gives out 10 CO2 plus 10 electron, and 5Fe2 positive gives out 5Fe3 positive plus 5 electron. Next reaction is 5NO2 negative plus 5H2O gives out 5NO3 negative plus 10 H ion plus 10 electron, and after that next reaction is 10I negative gives out 5I2 plus 10 electron. The full reaction can be written by adding the half reaction for KMnO4 to the half reaction of the reducing agent, balancing wherever necessary. If we present the reduction of permanganate to magnate and manganese dioxide to manganese second salt by half reactions, then the reactions are MnO4 negative plus electron gives out MnO4 2 negative, MnO4 negative plus 4H ion plus 3 electron gives out MnO2 plus 2H2O, and MnO4 negative plus 8H ion plus 5 electron gives out Mn2 positive plus 4H2O. We can very well see that the hydrogen ion concentration of the solution plays an important part in influencing the reaction. Although many reactions can be understood by consideration of redox potential, kinetics of the reaction is also an important factor. Permanganate at H ion is equals to 1 should oxidize water, but in practice the reaction is extremely slow unless either manganese second ions are present or the temperature is raised. A few important oxidizing reactions of KMnO4 are given below. Number 1. In acid solutions. A. Iodine is liberated from potassium iodide. 10I negative plus 2MnO4 negative plus 16H ion gives out 2Mn2 positive plus 8H2O plus 5I2. B. Fe2 positive ion green is converted to Fe3 positive yellow, and the reaction is 5Fe2 positive plus MnO4 negative plus 8H ion gives out Mn2 positive plus 4H2O plus 5Fe3 positive. Next reaction is oxalate ion or oxalic acid is oxidized at 333 K. 5C2O4 2 negative plus 2MnO4 negative plus 16H ion gives out 2Mn2 positive plus 8H2O plus 10 CO2. D. Hydrogen sulfide is oxidized, sulfur being precipitated, and the reactions are H2S gives out 2H ion plus S2 negative. Next reaction is 5S2 negative plus 2MnO4 negative plus 16H ion gives out 2Mn2 positive plus 8H2O plus 5S. E. Sulfurous acid or sulfide is oxidized to a sulfate or sulfuric acid, and the reactions are 5SO3 2 negative plus 2MnO4 negative plus 6H ion gives out 2Mn2 positive plus 3H2O plus 5SO4 2 negative. F. Nitrite is oxidized to nitrate. 5NO2 negative plus 2MnO4 negative plus 6H ion gives out 2Mn2 positive plus 5NO3 negative plus 3H2O. Number 2. In neutral or faintly alkaline solutions, A. A notable reaction is the oxidation of iodide to iodate. 2MnO4 negative plus H2O plus iodide negative gives out 2MnO2 plus 2OH ion plus IO3 negative. B. Thiosulfate is oxidized almost quantitatively to sulfate, and the reaction is 8MnO4 negative plus 3S2O 2 negative plus H2O gives out 8MnO2 plus 6SO2 2 negative plus 2OH ion. C. Manganese salt is oxidized to MnO2. The presence of zinc sulfate or zinc oxide catalyzes the oxidation 2MnO4 negative plus 3Mn2 positive plus 2H2O gives out 5MnO2 plus 4Hin. Note, paramanganate titrations in presence of hydrochloric acid are unsatisfactory since hydrochloric acid is oxidized to chlorine. Uses. Besides its use in analytical chemistry, potassium permanganate is used as a favorite oxidant in preparative organic chemistry. It uses for the bleaching of wool, cotton, silk and other textile fibers, and for the decolorization of oils are also dependent on its strong oxidizing power. The inner transition elements, F block. The F block consists of two series, lanthanoids, the 14 elements following lanthanum, and actinoids, the 14 elements following actinium. Because lanthanum closely resembles to lanthanoids, it is usually included in any discussion of the lanthanoids for which the general symbol Ln is often used. Similarly, a discussion of the actinoids includes actinium besides the 14 elements constituting the series. The lanthanoids resemble one another more closely than do the members of ordinary transition elements in any series. They have only one stable oxidation state and their chemistry provides an excellent opportunity to examine the effect of small changes in size and nuclear charge along a series of otherwise similar elements. The chemistry of the actinoids is, on the other hand, much more complicated. The complication arises partially owing to the occurrence of a wide range of oxidation states in these elements and partially because their radioactivity creates special problems in their study. The two series will be considered separately here. 8.5. The lanthanoids. The names, symbols, electronic configurations of atomic and some ionic states and atomic and ionic radii of lanthanum and lanthanoids for which the general symbol Ln is used are given in table 8.9. 8.5.1 Electronic configurations. It may be noted that atoms of these elements have electronic configuration with 6s2 common but with variable occupancy of 4f level. However, the electronic configurations of all the tripositive ions, that is the most stable oxidation state of all the lanthanoids, are of the form 4Fn, where n is equals to 1 to 14 with increasing atomic number. 8.5.2 Atomic and ionic sizes. The overall decrease in atomic and ionic radii from lanthanum to lutetium, the Lanthanoid contraction is a unique feature in the chemistry of the lanthanoids. It has far-reaching consequences in the chemistry of the third transition series of the elements. The decrease in atomic radii that is derived from the structures of metals is not quite regular as it is regular in M3 positive ions. This contraction is of course similar to that observed in an ordinary transition series and is attributed to the same cause, the imperfect shielding of one electron by another in the same subshell. However, the shielding of one 4f electron by another is less than 1d electron by another with the increase in nuclear charge along the series. There is fairly regular decrease in the sizes with increasing atomic number. The cumulative effect of the contraction of the lanthanoid series, known as Lanthanoid contraction, causes the radii of the members of the third transition series to be very similar to those of the corresponding members of the second series. The almost identical radii of ZR, that is 160 pm and HF 159 pm, a consequence of the lanthanoid contraction, account for their occurrence together in nature and for the difficulty faced in their separation. 8.5.3 Oxidation states. In the lanthanoids, La2 and Ln3 compounds are predominant species. However, occasionally, +2 and +4 ions in solution or in solid compounds are also obtained. This irregularity, as in ionization enthalpies, arises mainly from the extra stability of empty, half-filled or filled F subshell. Thus, the formation of Ce4 is favored by its noble gas configuration, but it is a strong oxidant reverting to the common +3 state. The E value for Ce4 positive / Ce3 positive is +1.74 volt, which suggests that it can oxidize water. However, the reaction rate is very slow and hence Ce4 is a good analytical reagent. Pr, Nd, Tb and Div and Dy also exhibit +4 state but only in oxides MO2. EU2 positive is formed by losing the 2 s electrons and its F7 configuration accounts for the formation of this ion. However, EU2 positive is a strong reducing agent changing to the common +3 state. Similarly, Yb2 positive, which has a F14 configuration, is a reductant. Tb4 has half-filled F orbitals and is an oxidant. The behavior of samarium is very much europium, exhibiting both +2 and +3 oxidation states. 8.5.4 General characteristics. All the lanthanoids are silvery white soft metals and tarnish rapidly in air. The hardness increases with increasing atomic number. Samarium being steel hard, their melting points range between 1000 to 12,000 K, but samarium melts at 1623 K. They have typical metallic structure and are good conductors of heat and electricity. Density and other properties change smoothly except for EU and YB and occasionally for SM and TM. Many trivalent lanthanoid ions are colored both in the solid state and in aqueous solutions. Color of these ions may be attributed to the presence of F electrons. Neither La3 positive nor Lu3 positive ion shows any color, but the rest do so. However, absorption bands are narrow, probably because of the excitation within F level. The lanthanoid ions other than F0 type, La3 positive and Cu4 positive, and the F14 type, that is YB2 positive and Lu3 positive, are all paramagnetic. The first ionization enthalpies of the lanthanoids are around 600 kJ per mole. The second about 1200 kJ per mole, comparable with those of calcium. A detailed discussion of the variation of the third ionization enthalpies indicates that the exchange enthalpy considerations, as in 3d orbitals of the first transition series, appear to impart a certain degree of stability to empty, half-filled and completely filled orbitals F level. This is indicated from the abnormally low value of the third ionization enthalpy of lanthanum, gadolinium and lutetium. In their chemical behavior in general, the earlier members of this series are quite reactive, similar to calcium, but with increasing atomic number they behave more like aluminium. Values of E for the half reaction is Ln3 positive plus 3 electron gives out Ln solid, are in the range of 2.2 to 2.4 volt except for EU, for which the value is -2.0 volt. This is of course a small variation. The metals combine with the hydrogen when gently heated in the gas. The carbides Ln3C, Ln2C3 and Lnc2 are formed when the metals are heated with carbon. They liberated hydrogen from dilute acids and burn in halogens to form halides. They form oxides M2O3 and hydroxides MOH whole thrice. The hydroxides are definite compounds, not just hydrated oxides. They are basic like alkaline earth metal oxides and hydroxides. Their general reactions are depicted in figure 8.7. The best single use of the lanthanoids is for the production of alloy steels for plates and pipes. A well-known alloy is miscamptal, which consists of lanthanide metal 95% and iron 5%. and traces of sulfur, carbon, calcium and aluminium. A good deal of miscamptal is used in Mg-based alloy to produce bullets, shell and lighter flint. Mixed oxides of lanthanoids are employed as catalyst in petroleum cracking. Some individuals Ln oxides are used as phosphors in television screens and similar fluorescing surfaces. 8.6 The actinoids. The actinoids include the 14 elements from TH to Lr. The name, symbols and some properties of these elements are given in table 8.10. The actinoids are radioactive elements and the earlier members have relatively long half-lives. The later ones have half-life values ranging from a day to 3 minutes of Lorentzium. The later members could be prepared only in nanogram quantities. These facts render their study more difficult. 8.6.1 Electronic configuration. All the actinoids are believed to have the electronic configuration of 7s2 and variable occupancy of the 5 and 6d subshells. The 14 electrons are formally added to 5f, though not to in thorium, Z is equals to 90 it is, but from Pa onwards, the 5f orbitals are complete at element 103. The irregularities in the electronic configuration of the actinoids, like those in lanthanoids, are related to the stabilities of F0, F7 and F14 occupancies of the 5f orbitals. Thus, the configuration of AM and CM are radon 5f7, 7s2 and radon 5f7, 6d1, 7s2. Although the 5f orbitals resemble the 4f orbitals in their angular part of the wave function, they are not as buried as 4f orbitals and hence 5f electrons can participate in bonding to a far greater extent. 8.6.2 Ionic sizes. The general trend in lanthanoids is observable in the actinoids as well. There is a gradual decrease in the size of atoms or N3 positive ions across the series. This may be referred to as the actinoid contraction, like lanthanoid contraction. The contraction is, however, greater from element to element in the series, resulting from poor shielding by 5f electrons. 8.6.3 Oxidation states. There is a greater range of oxidation states, which is in part attributed to the fact that the 5f, 6d and 7s levels are of comparable energies. The known oxidation states of actinoids are listed in table 8.11. The actinoids show in general +3 oxidation state. The elements in the first half of the series frequently exhibit higher oxidation states. For example, the maximum oxidation state increases from +4 in TH to +5, +6 and +7 respectively in Pa, uranium and Np, but decreases in succeeding elements. The actinoids resemble the lanthanoids in having more compounds in +3 state than in the +4 state. However, +3 and +4 ions tend to hydrolyze because the distribution of oxidation states among the actinoids is so uneven and so different for the former and later elements. It is unsatisfactory to review their chemistry in terms of oxidation state. 8.6.4 General characteristics and comparison with lanthanoids. The actinoid metals are all silvery in appearance but display a variety of structures. The structural variability is obtained due to irregularities in metallic radii, which are far greater than in lanthanoids. The actinoids are highly reactive metals, especially when finely divided. The action of boiling water on them, for example, gives a mixture of oxide and hydride, and combination with most nonmetals takes place at moderate temperatures. Hydrochloric acid attacks all metals, but most are slightly affected by nitric acid owing to the formation of protective oxide layers. Alkalis have no action. The magnetic properties of the actinoids are more complex than those of lanthanoids, although the variation in the magnetic susceptibility of the actinoids with the number of unpaired 5f electrons is roughly parallel to the corresponding results for the lanthanoids. The latter have higher values. It is evident from the behavior of the actinoids that the ionization enthalpies of the early actinoids, though not accurately known, but are lower than for the early lanthanoids. This is quite reasonable, since it is to be expected that when 5f orbitals are beginning to be occupied, they will penetrate less into the inner core of electrons. The 5f electrons will therefore be more effectively shielded from the nuclear charge than the 5f electrons of the corresponding lanthanoids. Because the outer electrons are less firmly held, they are available for bonding in the actinoids. A comparison of the actinoids with the lanthanoids with respect to different characteristics, as discussed above, reveals that behavior similar to that of the lanthanoids is not evident until the second half of the actinoid series. However, even the early actinoids resemble the lanthanoids in showing close similarities with each other and in gradual variation in properties which do not entail change in oxidation state. The lanthanoid and actinoid contractions have extended effects on the sizes and therefore the properties of the elements succeeding them in their respective periods. The lanthanoid contraction is more important because the chemistry of elements succeeding the actinoids are much less known at the present time. 8.7 Some applications of D block and F block elements. Iron and steels are the most important construction materials. Their production is based on the reduction of iron oxides, the removal of impurities, and the addition of carbon and alloying metals such as chromium, manganese, and nickel. Some compounds are manufactured for special purposes such as TiO for the pigment industry and MnO2 for use in dry battery cells. The battery industry also requires Zn and Ni or cadmium. The elements of group 11 are still worthy of being called the Coinage Metals, although Ag and Au are restricted to collection items and the contemporary UK copper coins are copper-coated steel. The silver UK coins are a Cu or a Ni alloy. Many of the metals and or their compounds are essential catalysts in the chemical industry. V2O5 catalyzes the oxidation of SO2 in the manufacture of sulfuric acid. TiCl4 with AlCH3 whole thrice forms the basis of Ziegler catalyst used to manufacture polythene. Iron catalysts are used in the Haber process for the production of ammonia from N2H2 mixtures. Nickel catalysts enable the hydrogenation of fats to proceed. In the Wacker process, the oxidation of ethine to ethanol is catalyzed by PdCl2. Nickel complexes are useful in the polymerization of alkynes and other organic compounds such as benzene. The photographic industry relies on the special light sensitive properties of AgBr. Summary: the D block consisting of group 3 to 12 occupies the large middle section of the periodic table. In these elements, the inner d orbitals are progressively filled. The F block is placed outside at the bottom of the periodic table, and in the elements of this block, 4f and 5f orbital are progressively filled. Corresponding to the filling of 3d, 4d and 5d orbitals, three series of transition elements are well recognized. All the transition elements exhibit typical metallic properties such as high tensile strength, ductility, malleability, thermal and electrical conductivity, and metallic character. Their melting and boiling points are high, which are attributed to the involvement of n-1 d electrons, resulting into strong interatomic bonding. In many of these properties, the maxima occurs at about the middle of each series, which indicates that one unpaired electron per d orbital is particularly a favorable configuration for strong interatomic interactions. Successive ionization enthalpies do not increase as steeply as in the main group elements with increasing atomic number. Hence, the loss of variable number of electrons from n-1 d orbital is not energetically unfavorable. The involvement of n-1 d electrons in the behavior of transition elements imparts certain distinct characteristics to these elements. Thus, in addition to variable oxidation states, they exhibit paramagnetic behavior, catalytic properties, and tendency for the formation of colored ions, interstitial compounds and complexes. The transition elements vary widely in their chemical behavior. Many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble of the first series. With the exception of copper, all the metals are relatively reactive. The transition metals react with a number of non-metals like oxygen, nitrogen, sulfur and halogens to form binary compounds. The first series transition metal oxides are generally formed from the reaction of metals with oxygen at high temperatures. These oxides dissolve in acids and bases to form oxometallic salts. Potassium dichromate and potassium permanganate are common examples. Potassium dichromate is prepared from the chromite or ore by fusion with alkali in presence of air and acidifying the extract. Pyrolusite or MnO2 is used for the preparation of potassium permanganate. Both the dichromate and the permanganate ions are strong oxidizing agents. The two series of inner ionization elements, lanthanoids and actinoids, constitute the F block of the periodic table. With the successive filling of the inner orbitals, 4f, there is a gradual decrease in the atomic and ionic sizes of these metals along the series, that is Lanthanoid contraction. This has far-reaching consequences in the chemistry of the elements succeeding them. Lanthanum and all the lanthanoids are rather soft white metals. They react easily with water to give solutions give +3 ions. The principal oxidation state is +3, although +4 and +2 oxidation states are also exhibited by some occasionally. The chemistry of actinoids is more complex in view of their ability to exist in different oxidation states. Furthermore, many of the actinoid elements are radioactive, which make the study of these elements rather difficult. There are many useful applications of the D and F block elements and their compounds, notable among them being in varieties of steels, catalysts, complexes, organic synthesis, etc. Chapter completed. Thank you so much. Students, please share this audio book as much as possible. हर बच्चे की जिससे मदद हो सके. Thank you so much once again. Bye bye.